Greetings and thank you for coming to check out our work, the development of predictive tools for assessment of natural attenuation capacity and treatment transition at chlorinated solvent sites, ER20-1079. I'm Natalie Capiro, an assistant professor at Auburn University, and working with me on this project are Dr. Kurt Pennell from Brown University, Dr. Mark Widdowson from Virginia Tech, Dr. Mike Kavanaugh, Dr. Eric Suckamel, and Dr. Claire Wildman, all from Geosynthetic Consultants. So this is a New Start project, and the objectives of this work are to improve our fundamental understanding of natural attenuation of chlorinated solvents at complex sites, those that are going to require remediation time frames in excess of 30 years. And we want to identify when to transition at these sites from active treatment to passive treatment. In other words, when can we focus on M&A? And ultimately, the goal is to develop predictive models and tools that can be used to support this transition decision, leading to more effective and more cost-effective management of these sites. So this is a New Start project. So prior to this work, we completed ER20-1079 that was led by Dr. Abriola in collaboration with myself and Dr. Kurt Pennell. And one aspect of this work was evaluating biologically enhanced back diffusion. This assessment was made in an aquifer cell, shown here on the left, which measures 60 centimeters in length and 40 centimeters in height. It's packed with a coarse sand, 2030 mesh Ottawa sand, and it has lenses of varying hydraulic conductivity and organic carbon content. The system was flushed with TCE, and measurements were taken following bioaugmentation. So here we were able to measure the difference between the measured concentrations shown here with the blue dots in these two bottom graphs, and then the red dashed lines show the predicted abiotic flushing that would be expected. So anything above that red line is what we're calling biologically enhanced mass transfer. And this mass transfer was impacted by the microbial reductive dechlorination, and it impacted back diffusion and desorption in these low permeability regions. And this was due in part to Halococoides mccartyi, which is one of the known strains that is able to transform PC or TCE all the way to ethene. They had entered into these low permeability regions and enhanced the attenuation in these zones. So overall in the system, we saw a cumulative bioenhancement factor of 12%, and the maximum of 53% and about 40% in the regions closest to the clay. If you'd like to find out more information about this work, please go check out our recently published paper in Chemosphere to find out more details. So now for the current work, this work combines laboratory experiments under Task 1 that are completed at Brown University by Kurt Pennell's group, and my group is focusing on the biological aspects at Auburn University. Numerical modeling under Task 2 that is being done at Virginia Tech by Mark Widdowson's group, and then field scale screening to estimate attenuation capacity, focusing on data mining, and that work is being completed at Geosynthetic under Task 3. So this is a New Start project. We're anticipating this is going to last for another, just started in August, we'll be going for another 3 or 4 years. So as under Task 1, this is the experimental component. We're looking at the combination of the biological, physical, and chemical aspects of natural attenuation, and we're really focusing on determining these rates of natural attenuation under conditions that are considered highly complex, so low permeability material. So at Brown University, they're doing the abiotic studies, and they're focusing on the sorption and desorption as a function of geochemical parameters, with an emphasis on non-ideal behavior. At Auburn University, we're doing the biological aspects of this work, and we're also under different geochemical conditions and assessing the role of microbial activity on this mass transfer from the low permeability regions. The work is being carried out in a series of different experimental systems ranging in scale from ampules that are flame sealed to maintain our good mass balance, and also the biological batch reactors and/or microcosms with field materials to, again, get those rates for transformation. And then the work comes together, both the chemical, physical, and the biological come together in these heterogeneous aquifer cells like described in the previous slide. Under task 2, this is the work being done in Virginia Tech, and this is focusing on the mathematical modeling to simulate these systems in these complex hydrogeologic settings. So right now, efforts are focusing on improving the existing models, specifically SEAM3D, by incorporating abiotic reactions and using the data collected under task 1 to validate those models. And then that information would then be incorporated into the efforts under task 3, the data mining, which are looking at a number of sites at the field scale to develop these predictions. So right now we're mainly focusing on developing or collecting a matrix of sites that could be used to compare to the data collected or determined under task 2 models. So again, it's a new project, so we don't have any results at this point, but we anticipate that this work will yield to better understanding of the relationships between coupled processes that govern long-term natural attenuation at these chlorinated solvent sites, develop mathematical models and predictive tools to better estimate that natural attenuation capacity and help to overall guide our better management of these chlorinated solvent sites. And of course, passing on this information in the form of tech transfer to remediation professionals and site management professionals so that they can make better decisions on selection of which sites are going to be amendable for this transition to active to passive from active to passive treatment. So specifically, what we're working on right now, I alluded to this when going through the task, was the sorption-desorption for under a variety of geochemical conditions under task 1A, and that's being done at Brown. At Auburn, we're looking at how the presence of microorganisms affect that sorption-desorption in these low permeability materials. Under task 2 at Virginia Tech, they're combining these models, looking at SEAM3D, MT3D, and ModFlow, and using the data collected under task 1 to validate those models. And then finally, under task 3, data mining efforts being conducted at Geosyntec. We're identifying real sites that have sufficient data density that can be used as inputs for task 2 and to help with benchmarking the natural attenuation capacity. If you'd like to find out more information, I have a website that is being developed at Auburn University, being managed under my laboratory's website. And then, of course, our contact information can be found there. So thank you for your attention, and I look forward to hearing more from you. Thank you.